welcome to this week's workshop. I'm excited to talk about reactions today. Hopefully you had a good 4th of July weekend. You may hear the little one, the 1-year-old, she's just having a rough morning. Got about an hour earlier than she normally does, and just been one of those mornings, which if you're a parent, I'm sure you are fully aware of. And so then also it's a bit of a crazy week around here for preparing for a 6-year-old birthday party on Thursday for my son. And so things are a little hectic, but I'm excited to spend this time with you. As always, look forward to hearing from you in the chat. Just click on the chat, type in a comment, and then I'll be able to respond from there. Let me pull up my chat real quick. And so with that, we're going to get rolling. And so today we're talking about chemical reactions, and it's one of those chapters that's very, very critical because it's the middle of what I call the big three. So reactions is, we've got nomenclature, we've covered that, we've already done a workshop on that, and then reactions leads into stoichiometry and moles. Or at least for me, I do those in order that way. And so for me, I do nomenclature first, then reactions, and conversions, and moles, and stoichiometry. And so reactions is kind of this middle part. It's this middle section. And so what we just talked about is kind of why I emphasize what I do, and kind of what's going to shape what I'm doing is that I'm trying to reinforce what we just learned in nomenclature while getting ready for conversions and moles and stoichiometry. And so I'm trying to set the stage for both of those, or reinforce one and set the stage for what's coming. So with that, let me turn off my video and I will get rolling with this presentation. All right, so most of you have been on before, but let me just go through it again. I grew up in Metro Atlanta, in the town of Marietta. We were known for the big chicken. It's a giant Kentucky Fried Chicken, big triangular chicken on top of a KFC. That's what we're known for in town. All the directions growing up were from, hey, we're 1 mile north of the big chicken, we're 1 mile south of the big chicken, that kind of thing. I then went to Georgia Tech, got my degree in chemical engineering, decided I did not want to be an engineer, decided I wanted to be a teacher instead. So I went back and got my education degree with a focus on chemistry. I've been teaching chemistry since 2001. Most of my teaching career in private schools, or all of my teaching career in private schools, most of it in small private schools, about 4 years in Atlanta, 4 years in Atlanta teaching kids with learning disabilities, and then 7 years at a Christian school in Jackson, Mississippi, and then another 4 or 5 years just at another small school. Well, actually a fairly large school, actually, for private schools sake. And then I left teaching a year ago to start this business, teaching high school chem, where it's my job to serve you. Just talking with some people this summer, just how chemistry prep can be that thing that just can kind of suck the life out of your school year. And I don't want that to do. I don't want chemistry to be that for you. I want to be there to equip you and help you with that. So that's why we're doing the summer workshop series and why I have my other resources as well. All right. So big first strategy when it comes to doing reactions, you got to have a firm foundation. We've talked about in these workshops about student-driven pacing, that you don't move on until the kids have a good grasp. And part of that involves breaking down into bite-sized pieces. That you break down things into small pieces, and then you assess those pieces before you move on to the next piece, and so on and so on. And so for this, we need to know what they need to know going in their reactions. So here's what they've got to know and what they need to have a good grasp on. They need to know their element names and symbols, and they've got to know their nomenclature, both ionic and covalent. If you want to throw in acids in there, that'd be fine. I don't cover that until I get to acids. I give them acid names at this point. But they've got to know nomenclature, because if you're trying to get a kid to work on a reaction and they're trying to figure out what to do for the formula, and it's still really time consuming for them, or something that they still get wrong 50% of the time, then they're going to have issues, and they're going to be behind the 8 ball. And so it's worth taking the extra time to make sure that they are really, really grounded here, because it just saves you headaches. Kind of like I said, this is what I call the middle step in a group of 3. And if I start trying to move on, if I start trying to build this floor before this one's strong enough to support it, it's going to collapse. And that's oftentimes what happens with some of our students is we try to move on before they're ready. And all of a sudden we get frustrated when it all collapses down and they're shutting down. They don't want to do the work. They think they're going to fail. All those things start coming into play. And a lot of that can be alleviated if we take the time to make sure we finish before we move on to the next floor. All right. So, second strategy is a version I've learned on balancing. What I learned was a method that was basically trial and error. You just kind of look at it and you try to figure out how to make everything equal. And I could kind of essentially, I'm really good at doing math in my head. And so I could count all of this in my head. And what's funny is a method that I learned here, that I'm going to show you here, this method. I remember showing it to another chemistry teacher. She's like, "Well, yeah, that's what we do." I'm like, "But no, you don't. You don't write it down. You just do it all in your head, and you try to, which for bright kids, our best and our brightest kids can balance reactions by looking at it. They really can, most of them, because they can do the math in their head. And so what I've got is a method that makes it more explicit, where you're actually writing down what you're counting. And so here's what it looks like. So when I first start teaching reactions, and I didn't do this at first, but that's one of those things I picked up as I just went along, is I started putting these dashes here. And the reason why I put those dashes there is so that kids learn where the coefficients go. Because if you've taught balancing before, you know full well that a kid's going to try to put a coefficient in here in the middle of the formula, or they're going to want to try to change the subscripts on the formula. Just common mistakes that kids make. But by putting these dashes in front and saying, hey, this is where the coefficients go, all of a sudden my kids are going to start making those mistakes a lot less. And so I don't have to worry about that as much. And it just makes things a little bit easier. But what we do is we count. We look at the reactant side, the left side, and we count. And then we look at the product side, the right side, and we count. Key thing here when they count is that they've got to count in the same order on both sides. Okay, so even though Cl2 is second, we write it third because that's how we wrote it over here. It's important that we do that, that they're in the same order on both sides. It just makes it a little bit easier to see. And so, and a lot of times I'll draw an arrow, this line down the middle. Just once again, I'm trying to help them delineate. This is reactants. This is products. Okay, and trying to delineate there. And so looking at this is actually not one that I would do first just because it involves doing common denominators. Lowest common multiple. So if you look at this, we need to make these be the same. So what can we multiply 3 by to get to the same thing that we multiply 2 by? Get them both to 6. So we multiply this one by 2. And this is where I'm teaching them that it applies to everything. It's not only 2 times the chlorine, it's 2 times the iron. So the iron also changes from 1 to 2. And we cross them out and we write them down here. Same thing with putting the 3 here. Gives me 6 chlorines, but it also gives me 3 magnesiums. And then usually they can pretty quickly figure out that I need a 3 and a 2 here to finish out the balancing. And so just a quick, easy method for doing balancing reactions. It's a method I teach them. I make all the kids do this at first, even my bright kids. And what I'm looking for is that by the time we get to the end of the unit, most of my bright kids don't have to write this stuff down anymore. And by the time we get to balancing and stoichiometry, most of my kids aren't writing this down at all. Most of them can look at it and do it in their heads. They get a sense of how it works. But this kind of gives them training wheels of a sort to learn how to go about doing balancing. Let's look at another example, because this has another one of the rules I like to teach my kids. So this is a combustion reaction of propane. So this is propane. I always forget propane and butane. I always get them mixed up. And so we've got C3H8 plus oxygen gives you carbon dioxide and water vapor. And so we do our counting. Okay, the thing here that is different though is this. an element shows up more than once on a side. In this case, it is oxygen. Oxygen shows up here in CO2. Oxygen shows up here in water. It shows up twice on this side. That's why there's 2 here plus the 1 there gives me a total of 3. So I always tell them to do it last because it's going to be the trickiest one. And so it's important that they kind of learn that strategy. So this is one of those strategies I like to teach. If an element shows up more than once, do it last. All right, so we do carbon first. So we had 3 carbons. We need to multiply this one by 3. Give me 3 carbons here. So 3 carbons. And then they got to count again. And this is where it gets tricky for kids with this method. And I really think for any method. But they've got to recount how many oxygens are on the side. And they want to do 3 times 3 is 9. I'm like, no. You're multiplying up here, not down here. This is just simply keeping count down here. So it's up here that you're actually doing the multiplying. 3 times 2 is 6, plus the 1 oxygen here gives me 7. Then they balance the hydrogens by putting a 4 here. So then once again, we recount the oxygens. 3 times 2 is 6 oxygens here, plus 4 oxygens here. 4 times 1 gives me a grand total of 10. Okay. Then I can go back and finish the oxygens by putting a 5 there. So by saving the oxygens for last, we're saving some headaches. So we do everything else first, then we come back and do that one last. And so that's just an easy method that kind of helps them know where to get started. All right, another situation that comes up, polyatomic ions. If a polyatomic ion is on both sides and it is the same, we have carbonate on this side, CO3. We have carbonate on this side, CO3. And so we can just treat it as one thing without having to break it up in the carbon-oxygen. Keeps it pretty simple. This one balances really fast, just needing a 2 here to balance out the sodium and the chlorine. All right, next example. If you've ever tried to balance this reaction, sodium with water or potassium with water, any of those alkali metals with water, it's kind of a pain. And it's one of those ones that can be very frustrating to students because the only thing that's out of balance is the hydrogen. But hydrogen shows up twice on this side. And it just makes it very difficult to get it to work. Once again, some of your brighter kids can probably figure this one out. And so I kind of created this next rule of just, it's one of those things I just learned by trial and error that works. And it is simply this. If you are struggling to balance a reaction, erase everything, put a 2 in the front spot, and start again. So put a 2 here, and so that forces the sodiums out of balance. That then now gives you something other than hydrogen to balance, which is going to make this end up working out a lot easier. So then you put a 2 here to balance the sodiums. And so now when I go to balance the oxygens, the hydrogens end up getting balanced too, and I'm done. So it's one of those things that, like, when a kid gets frustrated, it's one of those things I can say, hey, stop, erase everything you got, put a 2 in front of the first one, and try it again. Which is why I always do balancing in pencil, by the way. And so I teach them to do that. But I also, at this point, and usually before this, I've already mentioned it, but sometimes this method will cause kids to have higher coefficients than they're supposed to. So like, for example, let's go back over looking at this one. Like if they, for some reason, had a 2, a 4, and a 2. That'd be incorrect because they need to reduce those down. And so we would want to make sure that they reduce those. So that it need to be 1, 1, 2, 1. And so I also teach them that because that's one of the byproducts of this method is kids can sometimes put the 2 there when it doesn't belong there, and they need to reduce when they get done. But it's not a big headache. It's just another way of doing it. And so for me, that's balancing by counting. And like I said, it's essentially training wheels. It gives the kids a structure to understand balancing everything out, understanding where the coefficients go, understanding not to change formulas, And so like there's so many little things they need to remember in balancing that this kind of one thing gives them a structure to do everything else. No, they can do the coefficient in the right place. They can do their counting. And once they get used to it, then they can start doing it without having to write it down. All right. Strategy number 3. I like making my kids identify the reaction types because I just think it's a good mental exercise. And so these are the 5 types of reactions I teach. You could do single displacement and double displacement or sometimes those are called single replacement or double replacement. That's how I learned them. But from what I can research I've done, the technical name is displacement. You can also see those sometimes referred to as redox reactions, oxidation reduction reactions. But that to me, that redox is more of a AP Chem, college Chem thing. It's not really, I think, a great topic for kids at this age in just general Chem 1. So I don't really mess with redox and oxidation numbers and all that. So the way I teach my kids to identify them is by looking at the reactants. Okay. And that's what I want them to do. Okay, so element plus an element is a combination reaction, just one product. If you have just a single reactant, that's decomposition. Element plus a compound is going to be single displacement. A compound plus a compound is double replacement. And then some type of hydrocarbon plus oxygen is always going to be combustion. And once again, I only do complete combustion. I don't do incomplete combustion. Once again, it's not needed at this level. They just need to be introduced to the idea of reactions and the idea of types of reactions and the idea of combustion. Yes, a lot of combustion is not complete and perfect, but I'm not trying to teach the kids all the little details. I think they just get lost. And so literally I would give them, I'm trying to remember if I've got a slide that shows you what this looks like. I think I remember to, yeah, so, no, all right. So literally I would just give them a list of reactions and they got dashes in front of them. And they just have to put in like a C for combination, D for decomposition, SD for single displacement, DD for double displacement, and X for combustion. And so they would just literally go through a list of reactions, like the one that we saw earlier about sodium and water. That's single displacement. Sodium plus water, H2O is a compound, gives me sodium hydroxide plus hydrogen gas. And so they see that as single displacement, element plus a compound. Or if I did sodium phosphate plus copper chloride, that would be Na3PO4 plus CuCl2. That would be double displacement. We saw the reaction with butane, C3H8 plus oxygen gives me this. You could even do something like, sorry about that, screaming kids. Or you could do combustion like C6H12O6. You could put an O here with the hydrocarbon. That's fine. But as long as kids see that and are able to predict the products. It's just a mental exercise. I think it's good for kids, but it's also essential for what I do next because I make them predict the products. They have to tell me what this is. All right. And the only way they can predict the products accurately is if they can tell me what type of reaction it is. The reason why I make my kids predict products is this. It reinforces nomenclature. That's the primary reason I do this. Because most of these involve doing ionic formulas. Because when I do combination reactions, I don't do the covalent weird ones. I do just ionic. So I do like magnesium. Magnesium plus oxygen gives me magnesium oxide. And they got to predict that the formula is not MgO2, which is what they want to do, because they see Mg plus O2, and they want to say, oh, I just sandwich those together and I get MgO2. And I'm like, well, no, what are the ionic charges? Well, magnesium's 2+. What's oxygen? 2 minus. So what's the formula? MgO. Right, bingo. Okay. So I'm reinforcing that ionic formula and writing ionic formulas. Decomposition, I usually do not do it. There are rules that work for these, but I generally don't mess with them. Like if you take a carbonate and you heat it up, it's going to give off carbon dioxide and leave you with the oxide. So calcium carbonate, heat it up, will give you calcium oxide plus CO2 gas being given off. There are rules for those kind of things, but I think I've got them predicting enough that I don't worry about them doing decomposition reactions. I just don't deal with it. Single displacement is where we use the activity series. If you're not familiar with the activity series, hopefully you are, but it's a list of metals or halogens, and in order for this reaction to occur, the one that's out here by itself has to be higher on the activity series than the metal that's here, and then it'll displace it. I use a silly illustration of somebody cutting in at a dance. If you're dancing with a girl and the scrawny kid comes up and tries to cut in on the dance, you're kind of like, no, I got this dance. Sorry about it, dude. Bye. But then if somebody comes in who's like, bigger and tougher, who's like biceps are the size of your thighs, that kind of person walks in and wants to cut in, you're going to get out of the way because you don't want to get pummeled. And so it's a little bit of a crude illustration. Like, it's not a great illustration, especially in the age of bullying and all that stuff, but it works. Kids get it that, when we look at an activity series, the one that's higher up is bigger and stronger in a sense and cuts in and takes the ion, the negative ion. And so that's how displacement works. In contrast, we use double displacement. They both trade partners. So both dance partners are trading partners. It's not really a cutting in. It's just simply more like square dancing, where everybody's trading partners. You can decide what you want to do here. There are solubility rules out there. I don't like them. Once again, at this point in time, because I'm asking my kids to identify the reactions, and because I'm asking my kids to predict the products, I feel like I'm asking a lot of them mentally already. So I don't teach them solubility rules, because that would just be one more thing on top of everything I'm giving them for them to memorize. And I feel like I'm giving them enough by making them predict products, balance the reactions, identify what type of reaction it is. Maybe I'm asking them to name something in there. Like, I'm giving them enough to do without having to worry about doing solubility rules on top of it. And so I give them a solubility table, and I teach them how to use it. Identifying what forms precipitate, you got to have something form a precipitate, a gas, or water in order for this reaction to occur. And so, we're working on identifying those things. What is one of those happening, or is it a no reaction? And then combustion's easy because it is every single time, always CO2 and water. Easiest one to predict every single time because it never changes. And so that's an important aspect for predicting products. All right, so this came up as I was interacting with some people last week where I talked about lab safety. Now, I wanted to give you some suggestions of reactions that are safe and easy, for you and the kids, but they're also easy cleanups, and they're cheap. And so these are just some suggested reactions that I would use for each type. So, for example, combination. Burning magnesium is a fun one. Makes that really bright white light. If kids stare at it, it'll damage their eyes. So depending on how good your kids are at not looking at things, you can do that. You can do rust. Just buy a handful of nails or something iron, spray them down with water on a Friday during class, and then come back on Monday and there should be rust there. And you can even weigh them before and after. How much did they weigh before? How much did they weigh after? Oh, it gained mass. How? Oh, the oxygen from the air made rust. Something got added to the iron. My favorite is this one. Good old hydrogen fireball is always fun. I do it within reason. My first couple of years, I was a little more adventurous, being young and all. I would literally fill a balloon with hydrogen, put it on the end of a meter stick, and then put a burning splint on the end of another meter stick and light it. Sounds a lot too much like a gunshot going off in a school for it to be a good idea. So I don't do that one anymore. What I do is one of the single displacement reactions that I'm going to show you gives off hydrogen. And if you do this in a test tube or in an Erlenmeyer flask, it makes a really good little pop sound, a little whoop, that'll kind of like startle the kids and they just think it's hilarious. And so that's a good one to do. I really enjoyed that one. It's a really simple one. And the byproducts of it are is water vapor. So nothing to clean up. Right, decomposition reactions. When I talk about it, I give my kids the example of carbonic acid, which is fizz. Carbon dioxide, when you dissolve it in water, forms carbonic acid. When it decomposes into carbon dioxide bubbles and water. And so that's a good one, explaining why a flat coat tastes kind of watered down, because one of the byproducts of this reaction is water. You can do electrolysis of water. 9-volt batteries with paper clips. They stick the paper clips in the water, and they will see the bubbles of hydrogen and oxygen being given off. It's pretty simple. You may have to add, depending upon how hard or soft your water is, you may have to add a little bit of an electrolyte of some kind, like a little bit of salt to the water, just to help it react a little bit better. But that's an easy one. And if you've never done elephant toothpaste, that is just, it's a good demo. I wouldn't do it I wouldn't have the kids doing it. This one's good for the kids to do. This one is a great demo. So you go get some strong hydrogen peroxide. If you don't want to order it from a chemical supply company, Sally, like a beauty supply store, like a Sally's, find their strongest peroxide they use for bleaching hair. Or go to a pool supply shop. They have even stronger hydrogen peroxide at a pool supply store. And you can get it there. And then you can use yeast as the catalyst, but the best catalyst is potassium iodide. That one you do have to order. So strong hydrogen peroxide, which is dangerous. That's why I only do this as a demo for me. So strong hydrogen peroxide, food coloring, and toothpaste. You put that in some type of flask or beaker. And then you make a pretty strong solution of potassium iodide. And then you mix them together, and all of a sudden it just comes bubbling out of it. You've seen it on Jimmy Fallon. They do really, really strong versions of it that like shoot out of the container. Mine are never that violent. Mine just come out of it kind of like somebody squeezing toothpaste. And it comes out of the flask. I do it in a cookie sheet or a baking sheet to catch all the stuff. But that's a really fun decomposition reaction going on there. And then I liked it here because one of the fun things here also, the bubbles are oxygen bubbles. And so what I show the kids is I take a burning splint and I'll stick it into the bubbles, and the splint will get brighter. But it won't make a pop. It won't explode. It won't catch on fire. And so I try to explain to them that oxygen is not flammable. Oxygen makes things that burn better, but it itself is not flammable. And I still have kids who like argue with me. And I'm like, guys, here's the deal. Oxygen makes up somewhere a little over 20% of this room, the air in this room. If it were flammable, every time you lit a match, 20% of the room would catch on fire. And they're like, oh. I'm like, yeah. So it's not flammable. It just makes things burn. You don't have oxygen, things can't burn. The more oxygen you have, the faster and easier things burn. Which usually sometimes I'll share about Apollo 1 and the astronauts that died in the capsule because they were in a pure oxygen environment and there was a small spark, and because it was pure oxygen, everything caught on fire very, very quickly and tragically. Right, single displacement. this is the one I was talking about. Zinc plus hydrochloric acid will give you hydrogen bubbles that you can then light on fire for this reaction. You need a pretty decent strength. You probably need, I'd say, at least 3 molar hydrochloric acid for this. I like to do this in a test tube if I have the students doing it, because I don't want large amounts of 3 molar hydrochloric acid around. You can probably go down to 2, but anything lower than that just too slow, and I find that to be good. This is my alternative to sodium and water. You can do sodium and water if you want. Do it as a demo. Do it in a safe way. I like this one better just because it shows the same reaction, but it's a lot more controlled. It's a lot slower, but it still fizzes and moves around on top of the water. It's still cool to watch. And if you add some phenolphthalein to the water, you can see you can show them that it's forming the calcium hydroxide. This is my go-to. This is the one I do the most. I do these two the most. Okay, but I have the kids do this one because you take some aluminum wire, stick it in copper chloride solution, and it's going to bubble and fizz. You're going to start getting that copper forming on the outside of the aluminum wire, and you can see the solution is going to change color from blue to colorless. And it's just a good reaction to show the kids. It is fairly exothermic, depending upon the concentration you use, meaning it's going to give off a good bit of heat, so kind of keep that one in mind. Once again, in a test tube, it works really, really well. And once again, if you use a strong enough concentration of copper chloride, it'll happen pretty quick, and you'll be able to see the color change in a class period. And so I like to use that one. Also, because the byproducts of this, the aluminum chloride can go down the drain with a lot of water, and then the copper you just filter out. And so it's a really quick, easy cleanup. You just got to make sure you don't have any copper chloride going down the drain. That cannot go down the drain. But it's a quick, easy cleanup, and that's part of why I like these. Double displacement. Baking soda and vinegar is one. Hydrochloric acid and sodium hydroxide with an indicator, phenolphthalein, changing color. But this is my go-to. Once again, I'm using copper chloride again. Copper chloride blue. It's going to be a blue solution. Sodium phosphate's colorless. It looks like water. You mix the two of them together, and you get if you add enough sodium phosphate, you should end up with a colorless solution, meaning all the copper's been reacted, but you get this blue precipitate that about the color of toothpaste gel is what it looks like. And when you filter it out, it looks like somebody squeezed toothpaste gel into the filter. And it's a great one, and then when it dries out, it looks like dried toothpaste. But once again, it's great cleanup. As long as there's no blue in the solution, meaning you added enough sodium phosphate, the precipitate can go in the trash can, and the liquid, well, it's double displacement. What happened? These trade places, so the sodium goes with chlorine, and you have salt water. That's all the solution is. Dump it down the drain. It's clean. Really, really simple reaction to do there that I like to do. Combustion. You can do butane or propane. I like to do candles. And paraffin wax is somewhere around this formula. I use that one just because it works out easy for balancing. But I just do a simple, they weigh the candle beforehand and they weigh it after. It works well to use it again in stoichiometry, where they got to actually calculate how many moles of candle got used up. Something along those lines is really helpful. And so for combustion, a candle is a nice, safe, controlled reaction where you're still doing combustion, but in a way that is safe. I've seen people light methanol or ethanol on fire and have kids doing that. I'm just like, that stuff spills while it's on fire, you've got major troubles. It's not worth risking a kid catching on fire or getting burned, in my opinion. And so those are reactions that I suggest. So these are, like I said, I use these reactions because they're simple, they're easy for me, they're easy setup, they're easy cleanup. Because setting up labs is a pain in the rear. Cleaning up labs is also a pain in the rear. And the easier we can make it on ourselves, the better off it ends up being. And so Sure. Are there really cool and better reactions for double displacement out there? Yeah. I mean, I love the lead and silver, ones where you mix things in and you're adding two color solutions and all of a sudden you get this bright yellow precipitate. It's like, wow, where did that come from? It's pretty, it's beautiful. It's a pain in the butt to clean up because you're dealing with a heavy metal. Um, and it's not worth the headache to me. And so I choose simple things that work, really easy to clean up, that kind of thing. All right, so the strategies this week were make sure they understand their nomenclature before you get started, and make sure they're really well grounded there. Balancing reactions by being explicit with the counting, because that'll give them a framework, the kind of those training wheels to help them know what they need to do. And then you've got predicting products and identifying reaction types. Once again, I think it pushes their brains. It helps them reinforce the nomenclature. They need to be exposed to how the activity series and solubility tables work. It's just great for that. Big thing I want to announce here is I have extended this workshop series into August. And so I've added three new, and I'm repeating one. So the workshops in August, because I know some people will be starting back in August. I know around here they start back right before this. I think they go back on the 2nd or the 1st. So I've moved these to Saturday afternoons. So instead of Mondays at noon Eastern, they're going to be Saturdays at noon Eastern in August. These still remain on Mondays, the July ones. So these will still be on Mondays, and then these will move to Saturdays at noon. Okay, so student engagement, the big one I'm going to look at on the 3rd. A number of people I've seen work at Christian schools. And one of the challenge of working at a Christian private school is how to integrate faith and science. And so that's something I've done in my career. So I'm offering a workshop on that one. I know that doesn't apply to everybody, especially if you're teaching in a public school. You're welcome to come and watch, but I know that specifically is down to a smaller group of people that applies to. My rules and kind of my way of dealing with teenagers, I like teenagers a lot, and I like talking with them, and I like working with them, and I think there are ways that make that easier, and there are ways that make that harder. And I'm going to share kind of really my main 3 strategies for making working with teenagers so much more delightful, to bring out the best in them and to draw them out. And then I'm going to repeat the first one I did on planning and pacing. But I'm going to probably add a couple of things in there, like give you a suggested pacing for the year. And like, hey, here's somewhere you could be first semester. First quarter, second quarter, third quarter, fourth quarter. Be a little more explicit with some ideas there. So I'm going to tweak that one around there for the 24. And so once again, I still have the other things I'm doing. One of the things I'm going to be doing is I'm going to be adding the option of having one-on-one coaching hours, kind of basically if you just need not to purchase an entire academy or purchase an entire crash course, but you just need to sit down with me for an hour. I'm going to be offering those coming out, probably by the end of the month. And so I'm adding some options there. And then I've got like a mini course that I'm working on that'll be available beginning of August as well. Just trying to give you all resources to help you grow as teachers. Because, I was talking with somebody, emailing back and forth this week with somebody who just teaching chemistry was sucking the life out of their teaching year, and making it miserable. And I just don't want that to happen, or I don't want lab prep to be something that just sucks it out of you. So I want to give you everything you can to not be stressed out with chemistry. And so those things are there. And so if y'all have any questions, just pop those in the chat. And if not, I look forward to talking to y'all next week. And next week's workshop is looking at how to set up your year. So this is looking at a lot of things like expectations, a little bit of pacing, and then just philosophy and ideas to save time with grading and labs and that kind of stuff. And so all of that will be next week.